السلام عليكم ورحمة الله وبركاته. Okay, let me share the screen. Okay. Let's see what you wrote. Okay. So I think this is where we stopped. This is where I stopped in my previous lecture. Okay. Now we have started discussing about weirs, flow over sharp-crested weirs. Okay. And we have different types. Okay. We have the V notch. I explain all this. Where we have contracted weirs. Okay. When the full width of the weir is not equal to the full width of the channel. Okay, so it is contracted. Okay. And when the crest is very sharp crested weir, and when it is broad, we call it broad crested weir. When the section is triangular with V notch, okay, and, so we explain that we're explaining flow over sharp crested weir. Okay, that we need to ensure this air. Okay, using aeration pipe if we okay, or if we are using contracted weir, it will be naturally ensured, that air is flowing on the side. Okay, so we try to avoid having submerged, okay, or having a weir in which we don't have the free flow. Okay, free flow, that is in which we have this air cavity. Today we are going to start our experiments and we will demonstrate all these flows in the laboratory. Okay. Mention that when we have submerged weir, it can increase the discharge by 25% and damage the structure. In contracted weir, air is restored naturally from the sides. Okay? And in suppressed weir, we use installed ventilation pipes to ensure free flow. Okay? So these are some samples of weirs: V notch, stipulati, rectangular, and these are also some of them. V notch, which is rectangular, we are having this is the angle. This is stipulati, in which side ratio is 4:1, and this is another contracted weir, it's rectangular. Now let's derive the equation for the weir, the flow equation, and then we move on. So here we'll look at the simple case of a rectangular sharp crested with suppressed weir. Suppressed meaning there is no end contraction. Okay? And we'll apply the energy equation at two different points here, point 1 and point 2. Okay, this is the weir, this is the head of the weir, and this is upstream, just upstream of the weir. Okay, we'll look at its stream line, A prime. This is the front, this is the side view, this is the front view. Okay, this is the front view. This is the crest height, and this is considering a small element at a distance h from the crest. Okay, which is at this point, at point 2. And analyze the flow. So we'll apply the energy equation of the 2 points, point 1, point 2. We assume that they are on the same horizontal plane. The elevation term will cancel out. Okay, so we have h plus v1, v1 squared over 2g is equal to small h plus v2 squared over 2g. So at point 1, h is the sum of the datum and pressure head on the streamline. Of the datum and pressure head on the streamline. And pressure head on the streamline, because this is the datum. We are considering this to be our datum. Okay. So point 1, I'm now considering this streamline, A prime. Now you remember what streamlines are, okay? Which is a line that is at all points tangential to the velocity vector. This we explained in fluid mechanics. It's a line that is at all points tangential to the velocity vector. And for steady flow, streamline and path lines are all the same. So it's a path, it's, tracing the particle movement, okay? So that fluid particle moving on this streamline will move, this will be the streamline will be equal to the path line. Okay? So at point 1, h is sum of the elevation of the streamline and the velocity head above the streamline. Or the pressure head, okay, the pressure head of the streamline, because this is a streamline, so the pressure head above it is, okay, so head is the total elevation of the streamline and the pressure head above it. At point 2, the pressure is assumed to be atmospheric after Weisbach, okay? And the flow over the weir forms an overspilling jet whose under and top sides are exposed to the atmosphere when the approach velocity v1 is disregarded. So when we disregard okay, at this point, because of the reduction in the cross-sectional area, the velocity at this point will be higher than the velocity here. Okay, so we can disregard v1. Okay, this is v2. Okay, this is far greater than v1. Okay, so v1 is very small. So if we disregard the approach velocity, we will have v2. So it will be the v1 squared over 2 will be 0. Okay, so we'll have v2 to be equal to 2g into bracket h minus h. Okay, and to find the flow rate for this small element, okay, we need to find the area. Okay? The area is what? It's the length times dh. Okay? And the flow rate is AV. So I have to go back here. dq is dA times V. Okay, V is already here, V2, and this is dA, which is LDH. So here we need to integrate after introducing a discharge coefficient to account for the inertia and shear losses. The total discharge is here. Normally we neglect inertia and shear losses. Why do we neglect shear losses in particular? Okay. If you remember in fluid mechanics, the flow is flow, the velocity profile. When you have a solid boundary, is maybe something like this. Okay. Look at this, maybe the velocity profile. On the solid boundary, it is 0 because of the no slip condition. Okay, and then the velocity increases. Okay, and it's maximum at the open surface for open channel flow. Okay, so you see when you move away from the solid boundary, the effect of shear stresses are reducing. Okay, they reduce. they become not pronounced to some extent. They may actually be neglected for practical purposes without introducing any error. Okay, that's why in this case we are neglecting the shear stresses, shear losses. Okay, because they will all introduce losses which are not accounted for. So to account for all these, losses, we introduce the coefficient of discharge, which I explained before in our previous lecture. Okay, which is simply the actual actual flow rate over the theoretical flow rate. Okay, and when we integrate this with respect to h, we can use substitution. Okay, we will arrive at this over 3 CD 2G L h to the power of 3 over 2. This square root affects only 2 and G. Okay? It affects only 2 and G. L h to the power of 3 over 2 are not affected by the square root. Take note. Okay? So this is now the flow rate of a rectangular weir. But the first thing for all these hydraulic structures, the first thing one needs to do is to calibrate. Okay, calibration. And calibration entails finding the constant for those hydraulic structures. The constant for weirs are the coefficient of discharge. Okay, so one must know the coefficient of discharge of a weir. Okay, if it is supplied, if it is going to be installed in a practical channel, then it needs to be maybe a model of it has to be created in the lab and the coefficient found. Or if it is supplied by a company, maybe they must have done maybe a pilot scale study with it and try to find the coefficient of discharge. But whatever is the case, the coefficient of discharge has to be known before accurate measurement of flow rate can be done using the weirs. All we need to do, you see, all these are constants. 2 over 3 CD 2G L is a constant. Only H is variable, which is the head of water just upstream of the weir crest. Okay, just upstream of the crest of the weir. Okay, so meaning this is just like called KH h to the power of 3 over 2. Okay, K is the constant representing all these terms. All these terms. Okay, only variable is H. Okay, so all we need to do is to go to the lab, vary the flow rate, and measure the head just upstream of the weir crest. Okay, and if we can do this, like this one will give us straight line equation from the, this is Q, this is H, okay, and the slope will be equal to K, and K is equal to this. Okay, so you can plug in L is a constant, so you can find CD from this. So this is like one way to find the coefficient of discharge. Flow rate can be carefully controlled in the lab by using pump. Okay, where you can read the value of the flow rate. Okay, and the head measurement can be done. This is exactly what we are going to do today in the lab. Okay, and then at the end we can find CD. CD is usually less than 1, but in few instances you may find it to be greater than 1. But more often than not, you find the coefficient of discharge to be less than 1. 0.8, 0.6, usually 0.6 for rectangular weir. Okay, for sharp crested rectangular weir, usually around 0.6, 0.7, they are about. Okay, it varies. And what is the physical meaning, the interpretation of the value of CD if you go to the lab and determine it? These are one of the questions that probably we ask in the lab, like to whatever you find, what is the meaning? Okay, let's go. You go to the lab, do the experiment, which we are going to do this afternoon. Okay, determine the coefficient of discharge CD will be equal to, let's say, 0.61. Okay, it is dimensionless. Okay, so what is the significance of this value? Okay, what is the significance of this value? This is about 61%, isn't it? This is about 61%, and that means that the actual discharge, is just 61% of the theoretical discharge, because CD is QA over QT. Okay, so QA, the actual discharge, is CD QT. Okay, so If CD is like 61%, it means the actual discharge you are going to measure, okay, is actually about 61% of the theoretical discharge, meaning the theoretical discharge, which is derived without CD, we have eliminated a lot of, we have neglected some terms that will make our value to be overestimated. But when we find the coefficient of discharge, it will help us to find the actual flow rate in the field, in which all factors are considered during the flow calculation. Okay, because the actual flow rate is what is, if you will go and measure the volume over time, will give you. Okay, so that's the actual flow rate. Okay. Now let's move on. Rectangular characteristic wear with end contraction. So this is the case for suppressed wear. For suppressed wear, it has no end contractions. What about if we have end contraction? We know the importance of end contraction, isn't it? With end contraction, you don't need the ventilation pipe. You don't need the ventilation pipe to ensure free flow. Okay? With end contractions, you will have air naturally coming from the side of the wear. Okay, but if you don't have end contraction, you need the ventilation pipes. Okay, so end contractions are very important. Okay, to maintain free flow for effective measurement of discharge using weirs. So when the wear length is less than the width of the channel, it is known as a wear with end contraction. When the length of the wear is less than the length of the width of the channel, this is the channel width. So if the length of the wear is just some, okay, so not covering the whole width. Okay, so we call it wear with end contractions. So this is plan. It can be something like this. Okay, so this is the wear. Okay, and it did not cover the whole width. This is end contraction. This is two end contraction. If you have one end contraction, you can have two end contractions or one end contraction. Okay, so to find the discharge for wear with end contraction, you use this formula now. L, we don't just use L with L minus 0.1 NH, where N is the number of end contractions. If both ends are contracted, like in this case, we use N equal to, if only one end is contracted, we use N equal 1. Okay, like this is suppressed wear and this is contracted wear. Okay, and this H are the same. Okay, it's only the formula that changes. Now, rectangular sharp-crested wear with velocity of approach. If you see in the derivation, we neglected the velocity of approach. Okay, we neglected the velocity of approach in the determine when applying the energy equation. Okay, and that will also introduce some error in the determination of the discharge. Okay, so but it will simplify the computation. If we want to include the velocity of approach, okay, for effective head loss, the effective head loss responsible for the discharge, okay, is the sum, the effective head responsible for the discharge is the sum of water head and the head due to velocity of approach. So if the latter is not very small, the limits of integration in the equation, from 0 to h will change. So instead of using from 0 to h, we now modify it from v naught squared over 2g to h plus v naught squared over 2g. And at the end, if it is contracted wear, we introduce this term. And then if we include the velocity of approach, instead of having just power of 2 over 3, it will now be h plus v naught squared over 2g all to power of 2 over 3 minus the velocity head term also to power of 2 over 3. Okay. V naught cannot be found unless Q is known. Okay, so what do we do? V naught, that's the velocity of approach, cannot be found unless Q is known. That's the equation is first solved by neglecting the velocity of approach to get the approximate discharge. Okay, that's determined to get the approximate discharge. And when we get the discharge, we now use it to find the velocity of approach and then substitute it here to get revised Q. When we get the revised Q, we also get new velocity. We revise V naught, okay? A revised value of Q is determined using V naught. This process is repeated until the final discharge is within 1% of the preceding discharge. So you repeat is an iterative procedure in which you repeat until QI and QI plus 1 becomes very close. They agree within 1%. Okay, so that is when you stop. We'll take an example here to demonstrate the application, to demonstrate a case when we have to include the velocity of approach. Because like I mentioned, the effective head responsible for the discharge is the sum of the water head and the head due to velocity of approach. Okay, so this is the water head, and this is the head due to the velocity of approach. Okay. More often than not, you know, in engineering, we normally like simplify our computations by trying to neglect some terms that will introduce some non-linearity or will make the computations very complex. Okay, so but we try to simplify, we try to neglect certain terms that we feel will not, I mean, they will not seriously affect the accuracy of the results. Okay, if they do, because so many equations, depending on the situation, there is one in which the accuracy cannot be compromised. So in that case, no matter what, I mean, the complex nature of the equation has to be taken care of and be effectively solved. Okay, but for demonstration purposes and what have you, usually you realize some analytical solutions, some simpler problems can be reduced. I mean, some problems can be reduced to simpler ones, so that complex, you know, mathematical formulations will not be there. Now, trapezoidal wear. The discharge in this case for it, trapezoidal wear, all we need to do is to divide it into two. If you divide it here, yep. So you have 1, 2, 3. 1, 2, this is rectangular. 1 and 3 is, if you join them together, gives you triangular. If you join 1 and 3, it will give you triangular, isn't it? So this is 1 and 3. Okay, so we now divide trapezoidal wear into two, into triangular wear and rectangular wear, and then sum the equations for triangular wear and for rectangular wear. Okay, simple. So the discharge is the sum of discharges over the rectangular section, okay, over the rectangular section with n contractions, and over the triangular section. Okay, you can see here it has n contraction. Okay, so over the rectangular section with n contraction and over the triangular section, and a trapezoidal wear with a side slope of 1 horizontal to 4 vertical is known as a Cipolletti wear. Okay, so when this is 1 to 4, okay, which is the side slope, 4 vertical, 1 horizontal, is just a ratio, okay, that will help us determine the geometry of the section. We will use this ratio in the next chapter to help us find the geometry of some channels. Okay, so this special type in which the ratio is 4 to 1 is known as Cipolletti wear. The distance through a Cipolletti wear is given by the Francis formula for a suppressed rectangular wear. Okay, for a suppressed rectangular wear in which the coefficient is increased by about 1%. So this is the Francis formula. Okay, the units are in English units, 3.367 L h to the power 3 over 2. Okay. Now discharge over rectangular wear, this is the formula which we derived. Discharge over triangular wear, you can also derive this using the same formulation, okay, using the same formulation as we did for the triangular, for the rectangular wear. So this is the formula for the discharge over triangular wear. Over trapezoidal, we add this one, Q1, let's say Q2. So Q here is simply Q1 plus Q2, okay? We simply added, you know, the formulas for the discharge in rectangular and triangular. Okay. Because in this case, this is a suppressed wear, okay, not with any contractions. So if it has any contractions, definitely, we will have to modify the length term, okay. And also, if we want to account for the approach velocity, we have to modify the head term h, okay, to include the velocity head. And this is an example in which we have a suppressed sharp twisted weir, 15 feet long. So the length is 15 feet and has a crest of 3 feet height. Okay, the crest height is 3 feet. Determine the discharge for a head over the crest of 25 inch. So this is the head over the crest. Account for the velocity of approach. Okay, so here we have the length 15. Okay, and we have the height of the weir, which we normally designate with A, and we want to find the discharge Q. And the head over here is 15 inch. An inch we need to convert because other dimensions were given in feet, so we need to be dimensionally homogeneous by converting inch to feet. And 1 foot is equal to 12 inches. Okay, so 25 over 12. So we converted the head to feet. Okay, and we have been provided with a coefficient of discharge 0.65. So for a suppressed weir, without approach velocity now, we use the formula to find Q. We neglect the approach velocity in the first instance because we have to use the discharge to find the approach velocity. Okay, so we neglected the approach velocity and found the discharge 156. Okay, and then we find the approach velocity now using the discharge that we found. The area here is simply what? Simply the length, because this is the length of the weir, and it is just upstream. Okay, so this is the length, which is the width, okay, and it is suppressed, then times the height. The height is going to be height of the weir plus the head over it, which is h, because it is going to be something like this. Let me see. Let's see. Water is flowing over the weir in this direction. Okay, so this is h and this is a, which is the height of the weir. Okay, so the area is going to be the length of the weir, which is the width, times the height. And the height is going to be the head plus a. Okay, so that's why here we have 15 times into bracket 3 plus 2.08. Okay, so this is now the initial approach velocity. Now we find the velocity head, which is v squared over 2g, which is this. Okay, and then we now go back to the flow equation and take care of the approach velocity in h. Okay, this is the formula when we want to use the approach velocity. Instead of using just h, we use h plus v naught squared over 2g, all to the power of 3 over 2, minus the velocity head to the power of 3 over 2. When we substitute, we find revised q. So this is q2. If we call this q1, and this is q2, you can see it has increased. This is 156, this is 159.8. And then we find the percentage error between q1 and q2, okay, which is the difference between the two values over the latest value. Okay, so this is just 1.9%. So meaning we have to do it again because they have to agree within 1% percentage error. So now to do it again, we now find new velocity v naught based on q2. This is based on q1. Okay, so we now find new v based on q2. Okay, and this is the new velocity, and this is the velocity head. So we now go back here and substitute to find q3. This is q3. Okay, so q3 It's now 163, and this is Q4. Okay, this is Q here, 163 point. Okay, this is Q4. This is 3.6. This was the 3.4. And when you find the percentage error between Q3 and Q4, you realize it is 0.2%, which is less than 1%. And hence, we now use the last value, which is Q4. Okay, so this is now the flow rate. Is it clear? All we did is simple. First, we neglect the velocity of approach and find the flow rate using the formula without the velocity of approach. When we find the rate, we now find the velocity of approach using the estimated flow rate that we found, which is Q1. When we found the velocity of approach, we find the velocity head, and then we now use the formula that incorporates the velocity head, which is this one, to find the revised flow rate. When we find the revised flow rate, we compare it with the previous one to ensure that they agree within 1% percentage error. Here they agree 1.9 percentage error. So we continue by what? By finding the velocity, by revising the velocity again based on the new Q, that is based on Q2, which is what we did, and then substitute the new value of the velocity head in the flow, find new Q, okay, and then compare the previous one with the current value of Q to see if they agree within 1% error, okay, and this is what we did, okay. Is it clear? Now we will another example here for a trapezoidal weir. Here we have a trapezoidal weir has a side slope of 1 horizontal to 4 vertical. So it is C-palliative weir. Okay. The head over the weir is 2.5 feet. When the discharge is 30%, when the discharge is 30 cubic feet per second. What is the weir length? Okay. Here we want to find the weir length and compare the result with the C-palliative formula. Use coefficient of discharge to be 0.2. Now here, the flow over the rectangular section, okay, we will divide it into two as usual because this is trapezoidal section, okay, so we divide it into contracted weir, rectangular weir, and triangular weir. So this is the flow over the rectangular section, which is contracted. So that's why we have N 0.1 NH, okay, which is contracted, N equal to here, and H equal to 2.5, okay, and L is what we want to find. So this is when we simplify. Okay, this is Q1, and then we go to find Q2. Flow over the triangular section. Here, then theta over 2 equals 0.25, okay, equals 0.25. And how do you determine that? The side slope is 1 to 4. 1 horizontal, 4 vertical, isn't it? 1 horizontal, 4 vertical. So now the side slope is 1 to 4. This theta is the angle here. Okay, it is the angle here. So what is this angle? This one is the theta over 2. So let's take one triangle. Let's isolate one triangle and apply our knowledge of geometry. This is 1 to 4. And this is the angle. This is theta over 2. Okay. So what is tan is, this is right angle, opposite over adjacent. So tan theta over 2 is equal to opposite over, which is 1 over 4, 0.25. Okay, I hope it is clear. So we use the side slope to obtain our angle. Okay, sometimes the angle can be given. It can just say, okay, although this is like for trapezoidal section, in which it is not like explicitly intended to be triangular weir. Okay, but if it were to be a triangular weir at the beginning, probably the angle may be given in some instances. Okay, in other instances, it may not be given, but even if it is not given, the side slope should enable you to determine the angle. Okay, so tan theta over 2 equals 0.25, and this is how we obtained it. Okay, so we just go to the equation for the triangular weir, okay, and substitute the value. Okay, and don't forget, this is the formula for the triangular weir. For the triangular weir, it has no term in head. In length, it has only the head above the crest. Okay, here we find Q, and to find L, the total discharge in the trapezoidal section is Q1 plus Q2, and the total discharge has been provided from the problem as 30 S. Okay, so the only unknown here is going to be L, which can be made to be the subject of the formula, which is 2.29 feet. And using the Cipolletti weir, because compare the results with the Cipolletti formula. Cipolletti formula provides Q equal 3.36 L h to the power of 3 over 2. So Q is provided, we need L, okay? And L, based on the Cipolletti formula, is 2.25. So they agree very close, okay? They agree very close to the Cipolletti weir, okay? To the Cipolletti-Francis formula, which is an empirical formula. Now, another example here, it says during an experiment in a laboratory, 0.05 meter cubed of water flowing over a right-angled notch. Here the angle is right-angled notch, means it is a triangular weir and the angle is right angle. And what is right angle? Right angle is 90 degrees, okay? Was collected in 1 minute. So the volume is 0.05 meter cubed collected in 1 minute. So the flow rate is 0.05 over 1 minute. So 0.05 meter cubed per minute, which we can convert to per second. Okay. And then if the head over seal is 50 millimeter, calculate the coefficient of discharge of a notch. Okay. So the head over seal is simply the head above the weir crest. Okay. So the head of the top of the tunnel. Okay. Where you have the highest height of the triangular section. So this is the formula. Q can simply be found by saying 0.05 meter cubed over 1 minute is 60 seconds. Okay, so we divide by 60. Okay, 0.05 over 60. Which is this one. Okay, so to give you exactly 0.00833. Okay, then the angle is 90 because it says right angled notch. Okay, right angled notch, it means 90 degrees. Okay, we want to find the coefficient of discharge, which is CD. And the height of water above the seal is 50 millimeter, which when converted to meter is 0.05. So we just find CD to be make CD to the subject of the formula, which turns out to be 0.63. Very simple and straightforward. It's another example. It says a rectangular channel is 1.5 meter wide, has a discharge of 0.2 meter cube per second, which is measured in right-angled V notch. So this is also another triangular triangular section, and angle is 90. Find the height of the V notch. Okay, find the height of the V notch. Maximum depth of water is not to exceed 1 meter. Assume the coefficient of discharge to be 0.62. So here you have flow taking place. We want to find the height. Let's say A. The V notch in cross section will have something like this. Okay, and then we have the height of water because above it, okay? And this height is not exceed 1 meter, okay? So this is a triangular formula, okay? And the flow rate has been provided. Q is provided, CD is given, theta is 90 because it says right angle, okay? So we first need to find the head of water above, okay? Which is H, okay? So we need to find H, this one, okay? So using this formula, we found H to be 0.45. And then we were told that, so what is A? Height of apex of notch from bed, which is A, is now going to be the depth of water, the total depth, minus H, minus the height of water over V notch. So it's going to be 1. We were told that the maximum depth of water is not to exceed 1 meter. Okay, so it's going to be 1 meter minus H. That will give us A, because it's simply A plus H will not be greater than 1 meter. So A is equal to what? 1 minus H. And H, we found it from this one, from the discharge formula over a triangular notch. Let me see what you are writing. Maybe you are asking a question, because if it's in the presentation mode, I cannot see what you are typing. So let me go and check. Yeah, C it units. Yeah, C is dimensionless. C is dimensionless because it is QA over QT flow rate. As long as the flow rates are in the same units, the Q will always remain dimensionless. Okay? Because it's ratio of quantities having of quantities of the same quantity flow rate. Okay, let me go back to the presentation mode. So I always tell you, all these calculations, what are we doing? We are trying to find the discharge. We are trying to use a hydraulic structure called weir to measure the discharge in streams, rivers, and channels. Okay, and I always tell you the importance of measuring discharge. We measure the discharge, for instance, for flood mitigation. Okay, if you realize there is so much flood taking place, when we measure the discharge, we can now estimate whether that um, channel is adequate or not. And also we measure the discharge for streams and rivers to plan for water resources development to a community, because it is from the discharge that we will compare the discharge with the water demand of the community and try to see if the discharge will satisfy the water demand of that community. So measuring discharge in any flow problem or in any, water resources system is very, very important. Okay. So just trying to remind you so that you don't just look at it as some mathematical exercise just to find Q, just to play around with numbers, just so you keep track with the significance of all these calculations and understanding their practical application. Now we have another hydraulic structure called flumes, okay, which we are also going to use in the lab, okay, which they are devices in which the flow is locally accelerated, meaning you increase the velocity because acceleration is the change in velocity over time. Okay, so the flow is locally accelerated by means of a lateral contraction in the channel sides or combining the lateral contraction with a hump in the channel. Contraction in the channel side, let's say this is like the plan, this is like a plan, contracting this area which is reduced here at the throat, and then it enlarges to the previous value. Okay, when the cross section is reduced, then to maintain the same flow rate, because Q equals AV, when A goes down, the velocity has to increase to maintain the same flow rate, isn't it? So it is locally contracted. And this happens also when it is contracted, the velocity increases. We will go to when we go to the next chapter, we'll begin to discuss about critical flow. Okay, critical flow. So critical flow is like generated. Critical flow is induced as a result of the contraction. Okay, so and here you can, the second one is you can introduce a hump in the channel bed. We will also see the hump. Hump is simply like this, okay, which we introduced in the channel bed, okay, which has the effective result of also reducing the cross-sectional area of flow. All these are generally, reducing the cross-sectional area of flow. And once the cross-sectional area of flow, the velocity is increased, meaning it speeds up, okay, it accelerates because it changes from lower value to a higher value. That is the acceleration. Okay, so the first type is known as a Venturi flume, which is when you have the lateral contraction, okay, the sides, okay, is known as Venturi flume or long-throated flume, and the equation for discharge through a flume is based on the energy principle. Okay, it's based on the energy principle, which is like the Bernoulli's theorem. And the flumes are designed to achieve the critical flow in the contracted throat. I mentioned this. They are designed to achieve critical flow in the contracted throat section, like for the Venturi flume. Here you have the critical velocity. We'll explain what is critical velocity, what is supercritical, and what is subcritical velocity in the next chapter, okay, which probably we are going to start today. Okay, so they are designed to achieve a critical flow in the contracted section. And have four advantages. They can operate with small head loss, okay, and they're insensitive to the velocity of approach. Okay, they are insensitive to the velocity of approach. Meaning the velocity of approach do not significantly affect their results. And they make good measurements without submergence as well as under submerged conditions. Because this is not like a weir in which you need to ensure free flow, okay? And there is no related sediment deposition. For a weir, because water is flowing, so sediment can accumulate here, okay, just on the other face of the weir. But for a flume, there is no problem of sediment deposition, okay, because even when you have a hump, it is not like a weir in which this is very smooth, the slope is very small that even the sediment can easily move on top of the hump, okay, without depositing. But for where you have issues of sediment being accumulated, okay, because normally for natural flows, you normally have, it carries along with it debris and all other particles, okay, that are sometimes dumped as a result of anthropogenic activities, human activities, okay. Now, pipe flow measuring devices. Pipe flow measuring devices, the hydraulic structures, we use them for open channel flow. What about for pipes? Okay, here we use three common devices used to measure the flow rate through pipes. We have the orifice meter, the nozzle meter, and the Venturi meter. Okay, the orifice meter, the nozzle meter, and the Venturi meter. Okay, Venturi meter is different from the Venturi flume. Okay, although the principle are somehow similar, but this is for pipe, okay, while that is for open channel flow. That's the Venturi flume, and these all operate on the principle of the Venturi flume, okay. These operate on the principle of the Venturi flume, in that a reduction in the flow area results in increase of velocity in accordance with the continuity equation. So in all these cases also, there is a reduction in the flow area, and when the flow area is reduced, the flow is locally accelerated, and the velocity increase causes a reduction in pressure according to the energy equation, okay. And the discharge for orifices, nozzles, and Venturi meters can be calculated using this or that. Here we have the coefficient of discharge introduced, and this is the pressure difference, and this is the depth of the orifice, and this is the depth of the pipe. Okay, planning, probably maybe your term project, you may use these ones. Okay, for your term projects, you may use the orifice, nozzle meter, and venturi meter, because I think we all have them in the lab. Okay, now these are the uh, schematic diagrams. This is typical orifice meter. Orifice, hole. Okay, it does have hole. This is a pipe in which you have hole using the pressure taps. Okay, you have hole. This is the orifice diameter D. If you remember in fluid mechanics, we mentioned about flow separation. Okay, wake region. We have wake and attached flow. So here you have wake region, which is there is energy generated, which sometimes can damage the structure. Okay, in the wake region. Okay, and this is a typical nozzle meter. This is a nozzle meter. Okay, and this is the venturi meter. This is the throat. Okay, this is the entrance. Okay, this is the throat section, and this is the outlet. So you can see this section is smaller. Okay, hence the flow is accelerated in that section. All right, any question? Okay, if we don't have any questions, we'll take a few minutes and come back. We'll continue with the next chapter. Okay. Yes, we're back. You can see about 2 guys left. Ahmad Al-Shumri and Yazid Al-Anzi. So, should all come back. Let's move on. Okay. There's a new chapter, conveyance systems. Okay. Conveyance, that's how to convey fluid or liquid from one point to another. Okay. And here we'll look at open channel flow. Then later we'll look at pipe flow. The intended learning outcomes at the end of this presentation of these slides, students will be able to understand different types and states of flow in open channel and design real boundary channels carrying sediment-free water. And, there are 2 modes of transporting water from one point to another: pipes and open channels. In pipes, the flow of water is under pressure, okay, whereas open channel flow has a free water surface. Even for the pipe flow, it can be under gravity, in which the gravity will enable, the flow of water in the pipes to be under pressure. Okay, but for open channel flow, it has a free water surface which is being acted upon by the atmospheric pressure. And the basic theory is the same for both kinds of flow, but there is an important difference in the boundary condition. Okay? Open channel flow is more difficult to deal with due to the presence of the free water surface. And you have also various possible configurations of the channel section and the changing position of the water surface with respect to time and space. While for pipe flow, you have the pipe flowing full at all times. So you don't have these variables do not affect pipe flow. So that's why the open channel flow is somehow more difficult to deal with. And thus, the treatment of open channel flow is somewhat empirical in nature. Okay, so normally we'll be using a lot of empirical formulations because we don't have like clearly analytical formulations for the open channel flow. Okay, although we have some analytical concepts, but more often than not, we fall back to empirical formulations. Okay, and by empirical here means you go to the lab, just like the Francis formula. You go to the lab, analyze various sections, various types, come up with some formula based on the laboratory observations, rather than analytical ones. That's based on the properties of the fluid and the geometry and some, sound scientific relationships, which is in the analytical formulation. You have the empirical formulation and the analytical formulation. You may need to read more on that if they are still not very clear to you. Okay. And an open channel can be a natural stream or a river. Okay, I always say here in Saudi Arabia we don't have the surface water resources is very poor because we don't have streams and rivers. Okay? We only have seas. Okay, around some of the coastal areas. So it can also be an artificial channel in the form of a canal, but we have artificial channel and canal, or flume, chute, culvert, tunnel, ditch, or partly filled pipe, conduit, or aqueduct of any shape. For pipe, or you can have open channel flow inside a pipe. When the pipe is not flowing full, we call it also open channel. When you have pipe flowing full, Why is it not? When you have pipe flowing full, this is pipe flow, but you can also have pipe on which the flow is not full. So you have open water surface, okay? So this is also open channel flow. Although the water is flowing or the fluid is flowing inside a pipe, it is not pipe flow, okay? This usually occurs for water supply, and this is usually for sewer, okay? Our sewerage, okay? Sewer is usually pipes are used to convey our sewerage, that's the wastewater, okay? But they don't flow full. Okay, so they are treated as open channel flows. Okay, under this section, we'll probably look at some of the sections, I mean, some of the computations using the open channel flow or the wastewater flow in pipes, okay, which is considered as open channel flow. Okay. But here in Saudi Arabia, we have many, channels, artificial channels, downtown, Hafrel, a lot of canals, channels, for drainage, and what have you. Okay? An artificial channel is commonly used to convey water from its source of supply to a distribution point. And then further distribution beyond this point is made through a network of pipes. Okay? An artificial channel, also in the form of a canal, is excavated either in a firm ground, such as a rock, or in erodible materials. Okay? Erodible materials like in sand. Sand can be eroded. It's an erodible material, while rock is not erodible. Okay, and you have irrigation canals formed in alluvial. Alluvial is soil formed in alluvial and other granular material, are erodible unless lined with non-erodible materials. For our channels, it can be lined or unlined. Okay, we line usually with concrete. Okay, we line the our channel with concrete. Lining it will avoid, sediment transport in the channel, because transporting sediment in our channel reduces the efficiency, reduces the efficiency of the channel. Okay, in designing erodible channels, consideration has to be given to the stability of the channel geometry, such that substantial scouring does not take place. Okay, when you have a rectangular channel, if it is dug in sand, there is tendency when fluid is flowing, it may eat away this side, okay? It will be expanding, it will be eating away the side, okay? And be carrying along the eroded debris along with the flowing fluid, okay? So, substantials, we need to ensure scouring does not take place. And how do we ensure scouring does not take place? We will limit the velocity of flow. Okay, if the velocity of flow is very high, then the fluid particle can take the fluid molecules can take away anything it comes in contact with. But if the velocity is relatively lower, then scouring effect can be controlled. We are going to see in the channel design, we try to limit the velocity to some maximum value, okay, to reduce substantial scouring, okay, to ensure substantial scouring does not take place. Although here in the design aspect, we are going to see for the design of the channel, we'll look at a simple case of that is made up of a line channel or non-erodible material, okay, and without sediment deposition. All other subsequent ones can easily be done by considering, sediment deposition, scouring effects, and all that. Now, elements of the channel section. In this case, we will be looking at channel itself, the cross section, the parameters, the determination of the area of this channel and all that. And then we'll go into the different types of flows, okay, and the computation of these types of flows. Mostly the uniform flow, the critical flow analysis. Now, elements of the channel section. The flow in an open channel is due to gravitational force, okay? Yeah, is due to gravitational force, okay? Because once 2 points are at different energy level, okay, different energy level. Oh, once I touch it, it is okay. 2 points at different energy level. So here they possess higher energy. I mean, potential energy here is lower than the potential energy here. Okay, so liquid flows from higher energy to lower energy level. Okay, so the difference in energy results in the flow of fluid. Okay, so and this is as a result of gravity, because potential energy is simply m. Not writing. mgh. Yeah, this is the potential energy. You can see gravity. Okay, and this is the height above a particular reference level. Okay, so gravity is what is enabling open channel flow. Like I said, you can have also gravity to facilitate flow in pipes. Okay, when you ensure that when you have a tank at higher elevation, okay, and then you connect the pipes. So this is the pressure head in the tank, okay, and then the pipe can easily flow in the pipes, okay. And this is also gravity, because you raise the tank above to increase the potential energy of the liquid, okay, to increase the potential energy of the liquid in the tank. So gravity is what is responsible for flow in open channel. Hence, the channel bottom should have a slope in the direction of flow, okay. Like if this is it, the slope of the channel should be such that it is also in the direction of the flow, okay? It should slope down in the direction of flow. Otherwise, if it slopes up, you cannot go against gravity without imparting energy to the fluid, okay? Like using fans or using pump, okay? You can go against gravity, but you need to impart energy, okay, to the flowing fluid using pumps. But if it is by gravity, then channels, they have to slope, okay, in the direction of flow. And a channel having varying cross section and constant bed slope throughout its length is not as a prismatic channel. Prismatic channel is simply a channel having constant cross section and bed slope. Okay, the bed slope is simply the slope of the bed. Okay, that is the channel bottom. Okay, this is the slope. Let's say, okay, we use S naught to denote the bed slope. Okay, so a channel having constant cross-sectional area and bed slope is known as prismatic channel. And the cross-section of a channel taken normal to the direction of flow at any point is referred to as the channel section. Okay, so the channel section, we are just defining terms here, okay, before we move to the actual computations. So the channel section here is the cross-sectional area of flow, which is normal to the direction of flow. We have the depth of flow, which is y, which is the vertical distance from the channel bottom to the free surface. You have the channel, water flowing, okay, so the vertical, okay, the vertical distance. And you have the depth of flow section, which is the depth of flow normal to the direction of flow. What are we saying? I think, do I have it here? Let me, yeah, so you can see this is the channel slope, okay, this is channel slope, and this is depth of flow, which is the depth of flow that is perpendicular to the flow section. And this is you have D and Y, depth of flow, which is Y, and depth of flow section, okay, which is D. This is the depth of flow, which is vertical, okay, which is vertical, irrespective of the channel slope. While the depth of flow section is perpendicular to the flow section, okay, which is aligned to the bottom, which is perpendicular to the bottom, channel bottom. While Y, so D here, you need to, as to the vertical, that is angle theta, okay, that is angle theta. So you may resolve it to find y. Y with respect to d. So y is going to be d1 cos theta. Okay. Y is going to be d1 cos theta if you resolve it. Okay. Or the other way around. Okay. D is going to be y cos theta. Okay. D is going to be y cos theta. This is y. Okay. And this is the slope. Okay. The channel slope is theta. Okay. Okay. So D is y cos theta. That's when you resolve y along D using theta as the angle, which is the bed slope. But the terms D and Y are used sometimes interchangeably because more often than not, the channel slope is usually very small. Okay, the channel slope, the bed slope is usually very small. And this we ensure that it is within certain limits, that is to avoid accelerated flow unnecessarily, because the higher the slope, the more the velocity of the flowing water in that channel. Okay, and top width is the width at the free surface. Okay, this is the top width. Is the width at the free surface T. Okay, and this is the side slope 1 to Z. Okay, this is the channel width B. Flow area, which is the cross-sectional area of flow, normal to the direction of flow. Rectangle is just breadth times the depth. Okay, the cross-section, and we have the weighted perimeter, which is across a channel section, the length of the channel surface in contact with water. The length of the channel section in contact with water. For rectangle, this is the length in contact with water. It's not the total rectangle, okay? It's just three sides of the rectangle, okay? If this is D, D, and this is B, it's going to be the weighted perimeter, going to be B plus D plus D, which is B plus 2D for a rectangle. Of course, it will vary from one section to another. For trapezium, for trapezium, for trapezoidal section, okay, like this. So it's going to be B plus the side slope, this the sides, okay. And how do you find this length? You use the side slope 1 to Z. The side slope will usually be given, okay. So to find the length, you normally used to use what is called the similar triangle, okay. Similar triangle. Okay? So if this is 1 to Z, the depth of flow Y is usually known, okay, and this side is usually, this is T, so this is usually known as well. So you can find this slanting side. We'll take some examples to demonstrate that. And we have the hydraulic radius, which is the ratio of flow area to the weighted perimeter. So R is A over P. And hydraulic depth, which is the ratio of the flow area to the top width. So D is A over T. And we have the section factor for critical flow, Z subscript C, which is A square root of D. D, don't forget, is the hydraulic depth, which is A over T. Okay. So the section factor for critical flow, we will use this in the design. Okay. And we have the section factor for uniform flow, which is A to the power of 2 over 3. R is the hydraulic radius, which is also A over P. Okay, so these section factors, we use them in the design of the channel. Okay, bear this in mind. We use the section factor for critical flow and the section factor for normal, for uniform flow. So this is like a front view, and this is the side view of a channel. Okay, 2 points, 1 and 2. Okay, and then see, this is this angle is theta. Okay, if this is d1, this is y, so you can resolve it, or along the section, and resolve y along d. Okay, so call it d1 is equal to y1 cos theta. Okay, we resolve it because this is the one perpendicular to the channel bottom. Okay, so d1 is equal to y1 cos theta. This is the channel section and the longitudinal profile. Still on the elements of the channel section, for a circular section now, okay, that was for open channel. Now for circular section, the geometric elements in the geometric elements in the dimensionless form as a ratio with an appropriate power of diameter are provided in 4.1. Okay, so here we use, the geometric elements in dimensionless form as a ratio with an appropriate power of the diameter, okay, d naught of the section. Okay, it provides a convenient means of determining the geometric elements for various depths of flow. Okay, and like I told you, for wastewater flow, which is considered to be an open channel, although we use pipes, okay, we use this usually the dimensionless form. Okay, so for a depth of flow of 0.94 d, section factor AR of 2 over 3 has a maximum value of 0.335 d naught to power of 8 over 3 in a circular section. That is discharge maximum at this depth. Okay, so here we are referring to circular sections that are considered to be open channel. Okay, so that's why the depth of flow is not full, because it's just 0.94% of the diameter. So this is the point when you have the maximum discharge. Okay, when flow is occurring in a pipe that is flowing not full. Okay, so the maximum discharge is obtained when the depth of flow is 0.94 d naught. And this is the geometric elements for a circular element. You have y over d naught, a over d naught power d naught squared, dw, r, e, and then we have the other. We will demonstrate the use of all this. Okay, you see maximum flow occurs at 0.94 full depth. So this is when we have the maximum flow. Okay. Now let's take some examples here. We have a circular section of 5 feet diameter. Okay, has a water depth of, the diameter is 5 feet, but the water depth is 3 feet. You can see it's not flowing full, like I mentioned. Determine the geometric elements. Determine the geometric elements. So from the given information, okay, the depth of flow y is 3 feet, okay, and the diameter, pipe diameter d naught is 5, okay. So y over d naught, y is the depth of flow, okay, y over d naught is 0.6. Now to determine the other geometric elements from the table, y over d naught is 0.6. We'll go to the table, y over d naught, which is the first term, is 0.6. So this 0.6 is happening here, okay. So we just draw a line and root of the other values. Simple. Okay, So A over D naught squared will be this value, which is exactly what we have here. A over D naught 0.494 is this value, 0.492. E over D naught will be 1.7722. R over D naught. This is because for circular section that is not flowing full, finding the area will be difficult, the weighted perimeter and the, all this, unlike a given cross section, let's say rectangular, trapezoidal, and all that. Okay, this is what we use to find, the flow parameters, the section parameters for a circular cross section which is not flowing full. Okay, so A over D naught squared. So from here we can find the area of flow. Okay, this is the area of flow. Okay, because we know D naught squared. We know D naught. To find the weighted perimeter, we just multiply out. Okay, to find the hydraulic radius, and this is the section factor. Okay, the section factor for critical flow. Okay, AD power of A into square root of D. Okay, this is the section factor for critical flow, and this is the section factor for uniform for normal flow. Okay, or for uniform flow. Okay. Section factor for uniform flow. Is a section factor for uniform flow. Okay, this is the value. Okay, and look at the unit as well. Okay. Look at the unit. This has unit 5/2 into this one 8/3 because of this one as well. Okay, so the unit is very important here. Now, types of flow. In mechanics, you were introduced to the different types of flow. Here, there'll be also some discussion on that, and some more information will be provided in that regards. So the flow in an open channel is classified according to the change in the depth of flow. Okay, according to the change in the depth of flow with respect to space and time. Remember, you have many parameters, of flow, or many parameters that control flow. In fluid mechanics, you often than not, we define the types of flow with respect to velocity, because velocity is one of the most important aspects. Okay? Then again, it's not only velocity, you have velocity, discharge, depth of flow, pressure, temperature. All these are flow parameters. So you can use any one depending on what you are talking about, okay, or depending on what you are interested in to describe flow. Okay. So in open channel flow are classified with respect to the change of the depth of flow with respect to space and time. So if the depth of flow remains the same at every section of the channel, the flow is known as uniform or normal flow. If it remains the same at every section of the channel, we call it uniform flow or normal flow. As well as if the velocity, we can also use velocity. If the velocity remains the same at every section in the channel, okay? In varied or non-uniform flow, the depth changes along the channel length, along the length of the channel. Okay. Just imagine this. This section 1, you have uniform flow because the depth here is equal to the depth here. Okay. So also the velocity will be the same. But from here, maybe you have a hydraulic structure and also the channel slope has changed. So you have non-uniform flow in this region. Then downstream, you also have uniform flow because the depth here is the same throughout. Okay. When the change in depth occurs abruptly over a short distance, abruptly here means suddenly. Okay, it is a rapidly varied flow. Okay, if it occurs rapidly. Okay, suddenly. Otherwise, it is a gradually varied flow. Like here, you have like a period when it is non-uniform, okay, which is some distance, okay. So we can call it maybe gradually varied flow, and you can also have rapidly varied flow. For instance, when you have certain change in the section, sudden obstruction in the flow direction, and all this, or sudden change in the bed slope. Okay, so all this will affect the flow parameters. They will affect the depth of flow. Okay, and they will affect whether it will become rapidly varied flow or gradually varied flow. Okay, gradually means the flow has changed over some distance, takes some time and distance to change. Okay. Probably if time permits, maybe I may add some things on this, okay, on the gradually varied flow aspect. Now, if the depth of flow does not change during the time interval under consideration, we call it steady flow. Meaning if the depth, if you fix a position at a given section, the depth of flow is the same. It doesn't fluctuate at all. Okay. Then we call it steady flow. And it is unsteady if the depth changes with time. Okay. For an unsteady uniform flow, the depth should vary, unsteady but uniform. So the depth should vary from time to time while always remaining parallel to the channel bottom. Okay. This is not a practically feasible solution. The depth will vary, yet always remaining parallel to the channel bottom. Okay, so this is not feasible to have unsteady uniform flow. Okay, so let's look at this again. It's just like a refresher of what you did in fluid mechanics. But in fluid mechanics, we tie the definition to velocity. Okay, here we are tying the definition because we are considering open channel flow. We are tying the definition of the types of flow to depth of flow. Okay, to the depth of flow. So for steady flow, you have flow occurring, and at every point in time, the flow parameters do not change with time. Meaning at any section, at any position, at any location, when you try to observe the flow, it doesn't change, the depth doesn't change with time. When we say depth, again, we mean the velocity is the same. I mean, at that section, it does not change. There is no fluctuation. For gradually varied flow, you can see when you put, let's say, a weir here, a dam, or something. So it will gradually accumulate and then it will change. Did you see the depth increasing with distance here? And when the depth increases, then definitely this is, we call it steady, gradually varied flow. Okay, steady, gradually varied flow. Because at a given section, the depth is the same. It doesn't fluctuate. Okay, at a given section, but it is non-uniform because the depth here is less than the depth here. For uniform, throughout the space, throughout the area or throughout the section under consideration, the area under consideration, the depth has to be the same. And you have steady, rapidly varied flow. Here you can have a gate, okay, in which water is flowing beneath it. Okay, and then it is accumulating and then it is moving. Okay, we will demonstrate all this in the lab. Okay, we will demonstrate all this in the lab. It is steady because the flow rate doesn't change with time, or particularly when you take a given section, okay, the depth of flow is maintained. Is maintained within a given interval of time. The depth of flow does not fluctuate, and this is definitely and you have unsteady flow in which the depth fluctuates with time, okay, at a given section. Like I mentioned, most of these flows we will demonstrate them. Okay, so this is steady, rapid, varied flow. Okay. Even the condition of steady uniform flow is difficult to obtain in natural channels due to irregular section, because steady can be obtained because the flow can be this, the depth can be not changing, but uniform, meaning the depth has to be the same throughout the cross section, throughout the channel section, throughout the channel. And that is difficult to obtain in natural channels due to irregular section. Okay, irregular section will now affect the depth of flow, and in artificial channels because of the existence of the controls. And controls here, you can have a weir for measuring, for measuring the flow rate and other flow controls. However, steady uniform flow is a fundamental type of flow that is considered in all channel design problems. So for design, we consider the flow to be steady and uniform. Okay, we mentioned clearly that it's difficult to obtain in natural channels, okay, because of the irregular section. And in the computation of flow in natural streams, the steady flow condition is assumed during the time interval under consideration. Unsteady flow relates to the propagation of a wave in the channel. Okay, unsteady flow relates to the propagation of a wave in a channel, in which you physically see it changing with time. Like I said, all this will demonstrate them in the lab. Okay, and types of open channel flow. Here you have the steady uniform flow, which can be demonstrated in a laboratory channel, and steady gradually varied flow, which usually takes place in irrigation and navigation channel, and steady rapidly varied flow, which can happen, which can be demonstrated for a flow over a weir or hydraulic jump. Okay, we'll talk about hydraulic jump later. Okay, an unsteady, gradually varied flow, which we have stream flow and flood wave, and unsteady, rapidly varied flow, where you have surges and pulsating flow. Okay, so these are some of the flows, but just remember, we mentioned that for design purpose, we consider the flow to be steady and uniform. Okay? It's a fundamental type of flow that we use for channel design problems. Okay, my time is up. I will stop here till we see in the lab. Any question before we call it, before we close? All right, thank you. See you in the lab.